Um, Hello, everyone. So I will be talking about the complexity of CSP-based ideal membership problem. This is joined with Andrei Bulatov. We both are from Simon Fraser University. I will start with some definitions like ideals, and then the problem statement, and then motivated task, and we will take it from there. So through this talk, we will be working with the ring of polynomials or with coefficients from a field, let's say reals or a complex number. And then an ideal is a set of polynomials that satisfies the following properties. So first, 0 belongs to that ideal. Then the ideal is closed under addition. Third, it absorbs multiplication. And the ideal membership problem asks the following. It is as follows. As an input, we have an ideal and a polynomial f, and the question is, does f belong to the ideal? Well, Hilbert-Bass's theorem says that every ideal has a finite generating set. So without loss of generality, we assume the ideal is given to us by a set of generators, f1 to fm. And when we say the ideal is generated by f1 to fm, it means like it can be every polynomial in the ideal is of this form, sum of hi fi's, I from 1 to m. Okay, so now we can formulate the problem as follows. As input, we have polynomials f and then f1 to fm, which generate the ideal. And then the question is, do there exist h1 to hm, polynomials h1 to hm, such that we can write f as the following sum, h1 times f1 plus all the way to hm times fm. Right. The search version, of course, is that to find these polynomials h1 to hm such that the equality holds. And in proof complexity, people call this type of proofs a Nullstellensatz proof of membership, or through this talk, we just call them membership proofs, right? But how do we solve IMP? So if we are interested in finding a proof, this is the case, then if this is the case, then unfortunately we cannot solve IMP by dividing f by f1 to fm, right? And then in order to have a proof of membership, we need another generating set called Grosvenor bases. So there's a set of polynomials that generate the ideal, but they are well behaved in terms of division. So in a sense, the remainder is unique if we divide by Grosvenor bases, and then the polynomial f, when divided by Grosvenor bases, if the remainder is 0, then the polynomial is in the ideal and vice versa. But there are several drawbacks with respect to these Grosvenor bases. For instance, they are sensitive to monomial order, and the only algorithm that we know for constructing them, namely Muckberger's algorithm, is quite tedious to analyze. But if we are only interested in the decision version of the problem, then we deal with the varieties. So what is a variety? A variety of an ideal is basically the set of all common zeros of polynomials in the ideal. Okay. Then a strong Nullstellensatz tells us that every polynomial that vanishes at every point of the variety belongs to the ideal. So for instance, if the ideal is generated by polynomial 1, then it's equal to the entire ring of polynomials and the variety is empty. All right. So in order to check to see if the variety is empty or not, we just need to check membership of 1. Okay. Let's see a toy example here. Now, let's say we are interested in two coloring of a triangle, the simple graph x, y, z, and colors with a loss of generality. Let's say colors are 0 and 1. So we want every vertex to be colored by 0 or 1. So we have these domain polynomials, for instance, x times x minus 1 equals 0, which says basically x must be 0 or 1. Also the same thing for y and the same thing for z. Then we need some polynomials that they capture or basically enforce the adjacency constraint. So basically that two adjacent vertices, they receive different colors. So for instance, for X and Y, because they are adjacent, then we encode such a constraint by the following polynomial, X plus Y minus 1 equals 0. And the same thing for the edge YZ and then the edge ZX, right? And of course, the graph is too colorable if and only if the polynomial system that we have here has a solution. Okay. Now, the ideal corresponding to this example that we have seen is basically putting all these polynomials together. And well, the graph has no two coloring if we can find a proof that one belongs to the ideal. And of course, in this case, we can find a proof that one does not one belongs to the ideal, and the one possible proof is as follows. Therefore, the variety is empty, and as we know, the triangle that we saw is not two color. All right. So the IMP is why do we care about IMP? This is at the heart of many proof systems. So as we saw here, IMP may provide witness that an instance has no solution, right? So we encode the problem using these polynomials, and then we check if one belongs to the ideal or not. And if we, well, and in some cases, we are able to find the proof of such a membership. And in proof complexity, people are interested in the size of such proofs, the smallest proofs. IMP also appears at the heart of algorithm design and approximation, where we work with sum of square proofs, a very strong and powerful framework for algorithm design and optimization. Let me briefly mention what do we mean here. So we are interested in minimizing this polynomial R subject to a set of polynomial constraints, P1 to PL. The system of polynomial, and then an SOS proof of that certifies that the R on this set of subject to this set of polynomial is at least theta is as follows. So if we can write down R minus theta as sum of a square polynomial, which is always greater than 0 because they are square polynomials, and then this ideal part, which is basically 0 over the variety, or basically the set of points that we are interested in working on. Then if we can find such a certificate, it tells us that R is at least theta on the subject to this polynomial system. So it turns out the bit complexity of the coefficients of the polynomials that are appearing in such SOS proofs when we are dealing with bounded degree proofs depends on the complexity of the IMP part. And this is due to Raghavendra and Weiss back in 2017. But so our goal here is to move towards a systematic study of IMP for combinatorial problems. Well, a framework which is quite expressive to express combinatorial problems is the framework of constraint satisfaction problems. And let me introduce the framework, and then we will take it from there. Gamma, a relational structure or a constraint language over a base set D from 0 to R minus 1. For instance, let's say the set is 0, 1, and then the inequality language over 0, 1 is basically this relation R, which has only two tuples, 0, 1 and 1, 0. Then the constraint language for 1 in 3 set problem has one single relation, and the relation is this three tuples that we see here, 0, 0, 1, 0, 1, 0, and 1, 0, 0, and so on. So, and then as soon as we have a gamma, we can define CSP, instances of CSP gamma. And instances of CSP gamma consist of constraint over gamma. And each constraint is basically a predicate over a subset of variables. And that predicate, of course, is coming from gamma. For instance, that the two coloring example that we saw is an instance of inequality over 0, 0, 1, right? So we have this inequality predicate over all these edges, x, y, y, z, and zx. All right, so now for any instance of CSP gamma, as we saw in the case of two coloring, we can construct an ideal. And the way that we construct the ideal is as follows. For every constraint that we have, we introduce a polynomial whose zeros are exactly the tuples of the from R, the predicate that we have. So we do that for all the constraints, and of course, for all the variables, we have these domain polynomials, as we saw in the 0, 1 case for two coloring. And then we put all these polynomials together. It gives us an ideal, right? And note that here the solution set of the instance, the CSP instance that we started with, is the same as the variety of the ideal that we construct here. All right, so now we can define ideal membership problem corresponding to a constraint language or a relation structure gamma. And here as input, we have an instance of CSP gamma with over some variables, x1 to xn, and then a polynomial f. All the question is as before, does f belong to the ideal that we construct from the instance P? And also, if you can, give me a proof of that membership. All right. And when the input polynomial has bounded degree D, we denote this problem as IMP sub D of gamma. Well, since we have this domain polynomials, the ideal is radical, and then we can use Nullstellensatz, weak Nullstellensatz, and we have an equivalent formulation for IMP. Well, as before, as input, we have a CSP we have an instance of CSP gamma and a polynomial. Now, well, we can rephrase the question and ask, is every solution of this instance of CSP a zero of the polynomials? And this immediately tells us that IMP of gamma belongs to the class of co-NP. All right. Well, there are several research questions regarding IMP and combinatorial problems, specifically in the framework of CSP. Let me mention a couple of them here. For instance, for which constraint languages or relation structure we can construct growth basis for every instance that is coming from that constraint language, or in which cases we have a small Nullstellensatz proof of membership for every instance that is from that particular type of CSP, from that particular type of constraint language, or in which cases the IMP can be solved in polynomial time. All right. Well, there are some known result with respect to Boolean IMP. This is due to Mastroianni and Mastroianni and Barati. So basically, they completely classified all the cases for the Boolean one, or the Boolean domain. So it says basically, if the constraint language has a majority polymorphism, which is the same as saying that we are dealing with two set instances, or if the constraint language has a semi-lattice polymorphism, which is equivalent to say we are dealing with horn or dual horn set instances, or if the constraint language has an affine polymorphism, which means we are dealing with the system of linear equations over GF2 or Booleans, then the IMP sub D is polynomial time, solvable for every D, and the tractability is by constructing Grosvenor bases. So in all these cases, you can construct Grosvenor bases of bounded degree and solve the problem. Otherwise, the IMP is co-NP complete. So what we are interested here is to study this algebraic stuff that have been developed for the study of CSPs, and see how they work for the IMP. So first of all, we can observe that if we add constant relations to our constraint language, the complexity doesn't change. This immediately tells us that if IMP of gamma is co-NP complete whenever CSP of gamma with all this constant relation is NP complete. Well, another thing is by the means of reduction between constraint languages. Right? We won't see, okay, is there a relation between constraint languages and the complexity of IMPs? So at the heart of this universal algebraic approach to CSP is the notion of primitive positive definability, or for short PP definition. So this basically says every relation from a constraint language can be expressed using a first order formula from relations from another language, right? So if this is the case between these two languages, then I have reduction between the corresponding IMPs, right? And this is the case where my constraint languages are over the same domain. And even a stronger notion of reduction between constraint languages, which is called PP, primitive positive interpretability, or PP interpretation for constraint languages that are over different domains, says that, well, basically I can find the mapping between these two domains, elements of these two domains, and after using this mapping, the relation from one language can be expressed using the relations of the other language, again by the means of PP definitions. Then there is a reduction, polynomial time reduction between the corresponding IMPs. This is quite strong and has very nice consequences, namely that we can focus on the algebras and polymorphism rather than talking about like particular constraint languages, right? So basically this PP definition tells us about polymorphism. And what are the polymorphism? So basically this polymorphism are identities that capture high order symmetry of relations. Okay, what does it mean? It means, okay, I have this relation, it has several tuples. If I apply this polymorphism on these tuples component-wise, it gives me another tuple from the relation. Or in another sense, if you have a couple of solutions, you apply this polymorphism component-wise on these solutions, it gives you another solution of the instance that you are working on. Very nice and powerful notion of symmetry. So basically this PP definition says there is something between polymorphism. And what we have is that more polymorphism that you have, your constraint language has, then the easier the problems tends to be, right? So the higher symmetry, more symmetry that there is in your constraint language, the easier the corresponding IMP is going to be. So we can forget about constraint languages and talk about only this polymorphism and algebras, right? So given this, we show that if we have a semi-lattice polymorphism over a domain, then the corresponding IMP for any language that is generated using that semi-lattice polymorphism is going to be polynomial. This means, so the semi-lattice polymorphism intuitively means there is a partial ordering on the domain. This is also if we have a dual discriminator, so polymorphism, which says basically your constraint language that is coming from this polymorphism has to be binary, and it has a particular nice properties. And then also in the affine case, then we can prove that every constraint, we can show, well, it's known that basically every instance can be expressed as a linear equation over GFP. And we prove in all these cases, the IMP sub D is polytime solvable. And what I'm saying here is only about the decision version, and we will talk about how to find a proof of membership. Let's see an example. Hopefully it gives us more intuition about what is going on. I am considering a semi-lattice case. We have a base 0, 1, 2, and then we have a semi-lattice operation which says 0 is less than 2, 2 is less than 1, 1 is less than 2, and there is nothing between 0 and 1. They are incomparable. And then we have another semi-lattice operation over 0 and 1, which basically says 0 is less than 1. Now, any instance or any constraint language that is generated and it's invariant under this operation, I want to find the reduction between their corresponding IMPs. Okay, so now we first need to transform the instances between their corresponding CSPs. Right? So let's say P is an instance of CSP-A and P star is an instance of CSP-B. Okay, how do we transfer? Consider this mapping between these domains. So which maps 0 to 0, 1, 1 to 1, 0, and 2 to 1, 1. Then in the instance P, we replace every variable X with a pair of variables, X1 and X2. And wherever in every constraint, we replace a value A for X with G of A for X1 and X2. And we add the constraint that X1 and X2 has to be 0, 1, 1, 1, or 1, 0. Then there is one-to-one correspondence between solutions of P and P star. And then the inverse of that mapping G can be interpolated by a polynomial. For instance, G inverse of X1 and X2 can be X1 plus X1 times X2. So now, given a polynomial f, an instance of CSP-A, P, we do two steps. One, we convert P into P star, and then we convert F into F star. How do we convert F? So we replace every variable X in the polynomial with G inverse of X1 and X2. This way, we can prove that F belongs to the ideal of P if and only if F star belongs to the ideal of P prime. All right, this is a nice trick which works for the decision version, but suppose we find a proof that says F star belongs to the ideal of P star. And the proof is as follows, as you see here. Then how can we find a proof for F being in the ideal of P? Well, we have messed up with these polynomials, right? We do this substitution, we change the domains. So it's absolutely non-trivial how we can recover a proof, right? Now, in the next part of the talk, I'm going to bridge a gap between this decision version and how to find a proof of membership. So in order to address this issue, we introduce an extension of IMP called XIMP. Here, as before, as in the input, we have an instance of CSP gamma P, and now we have a set of polynomials, L polynomials, F1 to Fn. Now the question is, does there exist C1 to CL, these coefficients, L coefficients, such that C1 F1 plus all the way to CL FL belongs to the ideal? And it turns out all the algebraic properties of IMP remains true for XIMP. Also, all the tractable cases of IMP remains tractable for XIMP. But why do we care about XIMP at all? Well, the beauty is here. It says if XIMP is polynomial time solvable, then there exists a polynomial. We provide a polynomial time algorithm that given an instance of IMP, it constructs a bounded degree Grosvenor basis, right? So if XIMP is polytime, then we can find a bounded degree Grosvenor basis. And remember, if we have Grosvenor basis, we can with respect to graded lexicographic order, that's important. If we have this Grosvenor basis, then we can find proof of membership, right? And how does this algorithm work? Basically, we enumerate all the monomials of degree at most d with respect to graded lexicographic order. And then for each of these monomials, we use XIMP to decide if a Grosvenor basis should contain a polynomial with such a leading monomial and find that polynomial, right? So this basically bridge the gap between decision version and search for a proof. And also it has applications for sum of square proofs and theta bodies. Please see our paper for this. Let me finish the talk by a couple of question as all future directions. So, but there is more between the CSPs, the techniques that have been developed for CSPs and IMP. So, for instance, consistency. What does it mean in terms of IMP? And what are more polynomial time problems in terms of this polymorphism? And what is this low degree restriction means in terms of CSP? Well, in terms of polynomials, well, it makes sense. We have low degree polynomials, but what does it say about the CSP? And then what are more consequences and applications of IMP in algorithm design and optimization? Well, I stop here. Thank you so much for listening to this talk. Thanks.